Okay, so this is Chapter 2, Section 2, and we're going to talk about acceleration today. Section 1 was about velocity, speed, instantaneous velocity, and we included into that formula, you've got distance or displacement. Now we're going to take this a step further. You've got another equation to add to that, and that is for your average acceleration. So if you have velocity or can find velocity, then you plug in velocity into acceleration and still over the time change. And that second bullet is telling you, well, what can change your acceleration? And you have got, if you have a change in speed, direction, or both, that means speed and direction, then you change your acceleration. And acceleration is a vector quantity because it also has to include direction.
An object changing speed is accelerating. The equation for acceleration is the change in velocity divided by the time required for the change. Acceleration can be calculated by knowing the initial and final velocities and the initial and final times. Like velocity, acceleration must also include direction. The velocity of this cyclist is increasing by 1 meter per second south each second. His acceleration is expressed as 1 meter per second squared south. If an object slows down and is traveling in a positive direction, the change in velocity is a negative value, so its acceleration will also be a negative value. If an object has a negative velocity, such as when the bicyclist heads the opposite direction and is accelerating in that direction, the acceleration will also be negative, even though the bicycle is speeding up. If there is no change in an object's velocity, its velocity is constant and its acceleration is zero. If an object has constant speed but changes direction, then its velocity is changing and it is accelerating.
So while we're looking at this, talking about when can it be positive or negative, and it's talking about the slope of your velocity time graph is average acceleration, and you can see where velocity and time are both plotted on this. You've got time, it's still on the x-axis, velocity is over here on the y-axis, a lot like our distance versus time graphs that you did in your lab that we had last time. It gives you 3 points. At point A, acceleration is positive. That seems pretty normal. B, there's no acceleration. At point B, so my question was, at point B it says there's no acceleration. The velocity is constant. Is your object actually moving at this point?
Yes.
It can still be moving, just at a constant velocity, which would give it a constant acceleration, so therefore there's no acceleration. And then part C, acceleration is negative, so that could be your velocity, your speed, you're slowing down. It could still be in a positive direction, but acceleration itself would be negative.
So if you face forward and then you pedal backwards.
Measures the rate of change in velocity. You can find the average acceleration of an object if you measure its velocity at 2 moments in time and divide the change in velocity by the time required to make the change. You can also determine the acceleration of an object from a velocity versus time graph of its motion. Consider an object whose motion is represented by this graph. Let's find the average acceleration for the time interval from 4 seconds to 10 seconds. Average acceleration is simply the change in velocity divided by the time of travel. In other words, the average acceleration equals the slope of a velocity versus time graph over a time interval. The acceleration at any moment, called the instantaneous acceleration, can be found by shrinking the time interval. As the time interval becomes infinitesimal in size, the value of the average acceleration approaches the instantaneous acceleration. The instantaneous acceleration at a particular moment in time is the slope of a line tangent to the velocity time graph at that time.
So they just talked about instantaneous acceleration. Do you find it basically the same way that you find instantaneous velocity?
Yes.
Yep, you still pick a point, you draw your tangent line, and it's the slope of that tangent line. So this is the chart that I was referring to about when do you know if acceleration is positive or negative. And it gives you several scenarios about, well, what's going on with your initial velocity. Is it positive or negative? What does that do to your acceleration? And what does that mean as far as are you speeding up or slowing down? So you can look through those. Obviously, the ones that are going to be the easiest to look at here are going to be, if velocity is positive, acceleration is positive, then you're speeding up. If velocity is positive but acceleration is negative, then you're slowing down. And then this one here at the bottom, if velocity is 0, acceleration can also be 0, then you remain at rest. So take a look at those before you try to answer some of your homework. Some just more symbols. We've already looked at all of these symbols, but we're going to put them into some formulas or equations that you need to know, and it gives you the relationship between time, displacement, velocity, and acceleration. And these are the equations. Let me point out something. On this slide right here, if we're looking at the equations, this first one, that is when your object has an initial velocity, so it's not starting at 0. But on this second set, they have just taken this equation right here, given you this equation, and that's where your initial velocity is 0. It says that your object starts from rest. So if your object starts from rest, then your initial velocity is equal to 0. So if you take VI out of this equation, aren't you left with what you see right here?
Yeah.
Yes. So although at first it looks like 8 separate equations, it's really the same 4 equations. Just 4 of them include if your initial velocity is not 0. And the 4 on the right are going to be, well, your initial velocity is 0, so you can take that part out of the equation. Make sure you write these down somewhere. Write them down somewhere because we will steadily be adding to them. You've already got 2 equations to add, the one for velocity and then the one for acceleration. And then you have these which they just swap them around depending on what you're actually given. Notice these first 3 all include, well, what if you have some kind of change in time that's given, something happens over a 2.5 hour period. There's your delta t. But the last one doesn't include anything dealing with time. What you're going to find out is sometimes it's as simple as just picking one equation and then using it, but oftentimes it's a combination of 2 equations. And let me tell you, at this point where you start to have multiple equations to pick from, especially if you have to put information in one equation, solve, and then put your answer into a second equation, oftentimes there's not just one correct method or way to do that. Okay?
Students, may I have your attention?
So coming up next is a sample problem. Instead of us going through all the details there within the PowerPoint, we're going to see if we can do this first. Again, lots of word problems are going to be given to you. I suggest, if anything else, if you get lost, write down all your given information and see, okay, what equation can I pick out of that I actually have a choice in this? So the person pushes a stroller and starts from rest. Automatically, what information is given? So your initial velocity is equal to 0, right? Uniformly accelerating at a rate of 0.5 meters per second squared. What was just given then?
Acceleration.
Acceleration is 0.5 meters per second squared. What is the velocity? What are we looking for? What's the symbol for that? What's the velocity after it's traveled? Oh, darn. Finishing up this problem, so it says what's the velocity of the stroller after it's traveled. So we are looking for final velocity. And it has actually traveled 4.75 meters. So that is going to be our distance, or delta x. And if we go back and we look at all of our equations, VI is 0, so we don't have to worry about it. When you go back and look at your 8 equations you got, you're looking at the 4 that are on the right when it says starting at rest. You do have acceleration. You do have delta x, but you do not have V sub f. And also notice that 3 of those 4 equations involve a change in time. So my question is going to be, before you move on, are we going to be able to pick one equation and solve, or are we going to need 2 different equations? So again, if you don't have time listed, if I look at the 4 equations, I do notice that the very last equation that is given to us, VF squared equals 2a delta x, we do have acceleration given, we do have delta x given, and we are trying to solve for VF. So at this point you're going to plug in your information and solve, and the rest of the PowerPoint will show you how they actually solve for this, but I'm trying to explain to you how do you pick out which equation do you use. So again, at this point it shows you the equation VI is equal to 0, so VI would cancel out of this. And then you solve, and your answer here is plus 2.18 meters per second. Again, VI in this one is 0, so you could have left it out from the very beginning.